Water erosion is a natural process by which soil is washed away by running water. It can be relatively minor, such as when topsoil is shifted around by rainfall, or it can literally reshape a landscape and cause flooding and landslides. This can cause a lot of problems for agriculture, but there are things that can be done to prevent at least some of the effects of water erosion. I'm Dr. DeBusk, and in this video, I'll discuss methods for reducing water erosion. All methods of controlling water erosion are based on one of four actions. First, reducing raindrop impact to lessen detachment. This can be done by growing vigorous crops that fill in the canopy quickly, leaving crop residues on the surface, mulching, or by growing a total vegetative cover. Second, reducing or slowing runoff. This lessens detachment by scoring and reduces the amount of soil that can be transported. Avoiding compaction, maintaining organic matter levels, and subsoiling help water infiltrate the soil. Contour practices and conservation tillage both reduce runoff. Third, carrying excess water off the field safely by use of grass waterways or tile outlets. Fourth, filtering soil particles out of running water. One could also distinguish conservation practices, things we do regularly to preserve soil like conservation tillage, from conservation structure, permanent modifications of the land like terraces. Most of these measures reduce erosion by several of the actions listed above, and many of these practices can be combined. While these conservation measures apply most directly to agricultural settings or production horticulture like vegetable or nursery production, water erosion can also occur in the grounds around homes and buildings. However, landscaping, properly designed, executed, and maintained, is itself a conservation practice. It covers the soil with vegetation, mulches, and other materials, and retaining walls are even a form of terrace. Practices that improve infiltration of water into the soil, thus reducing runoff, diminish erosion rates. Foremost among these are practices that increase soil organic matter content and improve aggregate stability. Organic agriculture, conservation tillage, cover cropping, and other practices can improve or at least preserve soil organic matter. Meadow crops most effectively improve aggregate stability, so crop rotations including meadow crops save soil as shown in the table. Voiding or treating compaction by subsoiling also improves infiltration, as do the biopores common to no-till soils. One might even consider lawn aeration a form of soil improvement. A newer version is the use of polyacrylamide, PAM, a synthetic water-soluble compound that can be sprayed on clay soils. At the molecular level, PAM consists of strands that bind clay particles together to stabilize soil aggregates, improving infiltration and reducing surface sealing and crusting. Vegetation cover protects soil from raindrop impact, standing in vegetation impedes overland flow, and root systems help bind the soil together. A standard erosion control practice is simply selecting a crop suitable for a site's erodibility. Nursery and vegetable crops offer the least vegetative cover and therefore are least suitable for sloping ground without protective measures. Small grains offer greater protection than common row crops, so including them in a rotation with row crops helps save soil. Permanent and complete vegetative cover, such as native prairie grasses or pasture, offers the best soil protection, so is the most suitable treatment for highly erodible land. Other forms of vegetative cover include cover crops, roadside vegetation, and turfgrass lawns. A well-maintained lawn with dense turf cover suffers negligible erosion, but a thin lawn may indeed erode. Conservation tillage sharply reduces sheet and rill erosion. It is the lowest cost conservation method per ton of soil saved. For these reasons, conservation tillage is the most widely accepted best management practice for controlling soil losses. The effectiveness of conservation tillage depends on a rough soil surface and surface residues, especially during the critical period before the crop canopy fills in. The definition of conservation tillage states that residue coverage must be adequate to bring erosion below T. 30% coverage is often taken as a minimum amount. Coverage can be measured directly by stretching a 50-foot cord marked every 6 inches diagonally across several rows. The number of marks touching a piece of crop residue is the percentage of coverage. For instance, if 35 marks touch crop residues, the coverage is 35%. This procedure should be repeated in several parts of the field and the results averaged. The figure shows the effect of several residue levels according to the Russell. In some settings, such as stabilizing slopes during new construction, mulching serves the same purpose of covering the soil to protect it. Contour practices include tillage and planting across slopes on the contour rather than up and down slopes. A contour is an imaginary line across the slope that remains at constant elevation. Water runs downhill perpendicular to these contour lines, so these practices prevent or impede that flow. Rainfall ponds behind the small ridges created by tillage, providing more time for water to infiltrate and impeding downhill flow. However, high-intensity rainfalls reduce the ridges, and high rainfall amounts can cause ponded water to overlap the ridges, which can be erased by water flowing over them. Therefore, areas of moderate slopes and low-intensity rainfall benefit most from contour tillage, as seen in the graph. Combining contour tillage with conservation tillage layers two technologies for greater protection. Strip cropping takes advantage of the fact that close-growing small grains and forage provide a dense vegetative cover, so protect the soil better than row crops. The photo shows strips of alfalfa alternating with corn on the contour. The distance of the less protected soil will be short, so less soil will be transported before entering the denser vegetative cover of the alfalfa strip, where water slows and soil particles are filtered out. Strip cropping adds another layer of protection to contour tillage and can be more effective in areas of moderate rainfall. Adding conservation tillage adds yet another layer of protection. A grass waterway is a shallow, sodded, wide ditch that runs down a slope. As shown in the top photo, water flow concentrates where opposing slopes meet. It is precisely in such places where a grass waterway may be installed. One of the waterways in the bottom photo illustrates this nicely. Since ephemeral gullies and gullies form here, grass waterways are a BMP for prevention of such gullying. Waterways are also designed to carry excess water off the field safely and may be used to collect water from tillage contours or terraces. Grass waterways are also a version of conservation buffer, described next. Strips of permanent vegetation that retard overland flow and act as living filters to remove sediment, nutrients, and pesticides are called conservation buffers. Conservation buffers reduce erosion and preserve water quality of nearby bodies of water. Conservation buffers also enhance wildlife habitat for ground nesting birds such as pheasants and other wildlife. Conservation buffers work by slowing runoff while improving soil physical properties so infiltration is improved. Contour buffer strips are strips of permanent vegetation planted on the contour between strips of cultivated crops. Filter strips lie along the downhill edge of a field and work primarily to filter sediment out of runoff from a field before it can enter a receiving area such as a nearby stream. Riparian buffers are strips of permanent vegetation along streams, wetlands, and other bodies of water to protect water quality from field runoff. Riparian buffers include versions with herbaceous plants like stiff grasses and woody plant buffers with trees and shrubs or some combination. Conservation buffers, like all other erosion control procedures, must be properly designed to function properly, taking into account slope length and other factors. An example of a design element is the width of a vegetative strip, which must be wider if more water can be expected to enter it. Where other measures fail to reduce erosion adequately, terraces may be built. Long or steep slopes on impermeable soil, for example, require terraces. Terraces are costly to install and are used most commonly for valuable crops or where there's a shortage of good land. In general, two kinds of terraces are used. Level terraces are parallel to the slope and do not empty into a waterway. This type of terrace is used where soil is permeable enough so that water can seep in once captured in a terrace. Graded terraces are needed where water cannot soak in enough. These may slope gently toward a waterway or be drained by an underground tile outlet. Several terrace designs are shown in the bottom figure. Of these designs, the broad-based terrace is most common. Terrace construction begins by designing them to fit conservation needs without overly hampering farming. The land is surveyed and the terraces are marked on the slope. Terraces must be properly maintained to ensure effectiveness. Terraces break up a slope into several shorter slopes. Diversions are large capacity terraces that divert runoff from higher elevations. Diversions are not farmed but are covered with grass. Our erosion prevention technologies were developed in response to conditions of a mid-20th century climate. Since climate is changing rapidly, many soil scientists are concerned that those technologies may be overwhelmed by climate change. Indeed, there is already some evidence of a quickening of erosion rates in some locations. Climate change models predict increasing in average temperature, greater frequency of extreme weather events such as prolonged drought, heat waves, or higher intensity storms, and changing rainfall patterns across the globe. We observe these climatic changes happening already, and they are likely to become more pronounced over time. For water erosion, a predicted increase in the number of highly erosive rainfalls in some locations will impact water erosion. Indeed, many of us have already experienced a marked increase in extreme rainfall events in recent years. Where contoured tillage has been a satisfactory way to control erosion, heavier rainfalls can erase the low contour ridges that tillage creates and render the practice ineffective. There may also be a shift from sheet and rill erosion to concentrated flow. A 2003 report from the Soil and Water Conservation Society predicted erosion increases as high as 90% on some cropland. Our erosion prediction models like Russell may no longer predict erosion as accurately. The iso-erodent map we use to determine the rainfall R factor will likely become inaccurate, as could other factors such as crop management factors, C. The report mentioned above suggests that climatic factors be updated immediately. Growers may need to alter their cropping practices in response to climate change. In conclusion, growing vigorous crops, maintaining organic matter, and avoiding overtillage and compaction help control erosion. Other strategies include conservation tillage, contour tillage, terraces, and buffers.